thing I want to do is I want to get a couple of the models. Let me make sure I can see that. A couple of the models we've collected in class so far. We've done a couple of experiments. So what I want to do is I want to get those models on the board because I want to wrap up exponential modeling today and then tie it into all the other kinds of modeling we've been doing. So that first experiment we did, number 1, was flipping the coin flips, yes? And if I remember correctly, the coin flip model ended up being y equals 21 or 19. I forget, we ended up having 2, didn't we?
Yeah, it's 21.
We'll just go with, it doesn't, either one's fine. 21 times
0.53
to the x power, where x is the number of flips that we took, and y, we defined it as the number of those remaining flipping, I think. I think that's how we defined it, yeah? Y was the number flipping at x flips. And the big takeaway here was, essentially, every additional flip taken, we lost half of the people that were flipping. Now, I think we came to peace with that, yes? We came to peace with that because why? Why did that make sense at the end of the day? Why were we losing half the flips every time? Go ahead, Aaron.
Because there's a 50% chance of getting heads.
Right, the whole idea was you flip until you get heads. If half the time you get heads, every single iteration, we're going to lose half of who's left. So we start with 20, it says 21, we start with 22, I think, that day. We lost, on average, 11 in the first. Then 11 flipped again, we lost half of them. Then 5.5 on average flipped, and we lost half of them, and then half and half. Jeremiah, ask me that question. Or just taking it all in?
Trying to figure out your abbreviations up there.
Oh, number of flips,
Okay.
number of flipping at x flips.
Okay.
Oh, here. Let's spell it out, sorry.
No worries.
I'm going all texting. Cool? So that was the first model. We'll come back to this. I want to come back and look at it and compare it to a theoretical, which we did in class that day. Then there was experiment number 2 and number 3, both of which we did last class. I've got number 4 and number 5 to do today, and then we're going to wrap the whole thing up in one big exponential package. Number 2 was keep drawing cards, excuse me. Draw cards until you get hearts. Right? That was the first experiment. So you keep drawing cards until you get hearts. So this was draw cards until hearts. And what was our model on that one? Y equals 21. Oh, excuse me. It wasn't 21, it was 20. Was it 20?
21.
Was it 21? It was. We had roughly the same. Okay, good.
0.7.
0.7, thank you.
X.
Excellent. And then we had X was the number of draws.
Trials.
Trials. Y is the number remaining after X trials. Love it. Did this make sense? Did the 21 and the 0.7, did we come to peace with why that made sense last time? What's the 21 out there in front?
Starting number.
Yes, we actually had 20, didn't we? But the model thought it was 21 based on because our data's not perfect. It's ish. So the idea is, the reason why 21 is here and 21 is also here, when we started the experiment, there were 21 of us on average, 22 or 20, depending on what day it was. But do you see mathematically why that makes sense? When the experiment starts, we haven't flipped at all. We haven't flipped at all, which means the number of flips is at 0, the number of draws is at 0. When you plug 0 into this model, look what happens. You get 21 times 0.53 to the 0 power. What's 0.53 to the 0 power? 1. What's 0.7 to the 0 power? What's 1/2 to the 0 power? What's 3 to the 0 power? Why? Why is anything to the 0 power 1 except for 0? You don't do 0 to the 0. Why? Why is it always 1? I love that, Michael. Has anybody ever been told why it's 1, or you're just told that it's 1?
We never get told why.
You never get told why? Oh my God, Amber, tell me that's not true.
Because it's accounting for that 0 place.
I love that. I love that, actually. Can we look at that as a pattern? Oh, Aaron, that breaks my heart. It doesn't surprise me, but it breaks my heart.
It's true.